In our puzzle, I thought we might have got to the end by 1350, because that seems an awful long time ago, 500, 600 years ago. And yet what we find is that already there are things happening by 1350, like an interest in time and the development of clocks, an interest in glass and the development of glass technologies in the West, which already seem to be something different and new in the world. So it looks as if, in order to understand this better, we're going to have to pull back further and wider, widen our time and our geographical scope. So how about trying going back 1,000 years, back to about 950, and see what we can find there. And again, looking at one or two things. One of them would be war and military technologies, because a lot of the discussion has been about the way in which the West finally pulverized the rest of the world using advanced war technologies. And the other might be something we haven't really looked at much, but is obviously important, is agriculture and ecology in an agrarian society before it develops into an industrial one. So let's have a look at those two things. Have a look at agriculture. Now, most people think that 1,000 years ago all the agricultural systems of the world must have been more or less the same. But in fact, there was already beginning to be a great divide. I work in the Himalayas in a community which grows basically as its main staple crop rice. And this is a crop which is a wonderful crop. It produces much more than the hard grains of Europe, like wheat. And it's also wonderful in that the processes of producing it, it's very time-consuming and labor-consuming in the production in the fields. You have to weed it and so on very carefully and plant it very carefully. But when you get to the stage of turning it into something edible, you have to get, once you've got the outer shell off, you just pop it in water, boil it, and you can eat it. Now, the hard grains of the West, which were already present in Roman civilization and were developed, are different. They don't take quite so much work, maybe, although the soil is very heavy and you have to plough it. Yeah. But certainly at the later stages, there's something very peculiar about them, which is that once you get them off the husk, you can't eat them. You have to grind them. You can make them into a kind of porridge with milk and so on, but it takes a long time and it's not very pleasant. So in order to make bread, which was favoured in the West, you have to mill it. And it's occurred to me that one of the great distinctions that begins to emerge, I know that China has a wheat belt in the north, just as India does, but basically there are other complicating factors, but one of the basic differences between Asia and Western Europe is in the basic grain, because once you have to start milling, if certain other things happen, like you forbid slavery, so that your milling isn't done by slaves, you begin to get interested in how we can save ourselves from all this work. An extreme case of this were the monastic orders, the Benedictines and the Cistercians. They had to produce their own food, they didn't have slaves, they had to also pray, so they tended always to build their monasteries next to streams and rivers so that they could use water power. So that the development of water power and later wind power and the development of animal power in the West is heavily related to the hard grains of the West. Whereas in Asia you get a tendency, it's not inevitable, but a tendency towards building up of populations to do the intensive work of planting and harvesting rice and weeding it. But after that you can do it all domestically, you don't need mills. So this is one difference which is already beginning to be apparent even 1,000 years ago, and it's going to have immense implications. So that's the simple hypothesis.
I would say that if we're looking at China around 900 AD, we are seeing an agricultural transition in full swing and already a long way along its route from the times where the population and agricultural production was largely in the north and was largely using things like dry wheat farming or dry millet farming, to the time when the population and economic activity in agricultural production had moved to the south, to the Yangtze Valley and away from the Yellow River Valley, and was concentrating, as you said, Alan, on the production of wet rice rather than dry grains in the north. And certainly it had many of the consequences that you have just outlined, that you do not need mills for this stuff once you've gone to the immense trouble of raising it, certainly. And while in the north there are still plenty of Chinese today whose main food is wheat, either in the form of noodles or in the form of breads of various kinds, steamed breads and so on, certainly by the time we have got past this mark point of 900 AD, increasingly the favourite food and overwhelmingly more and more the everyday food of most Chinese people who mostly live in the southern half of the country is rice.
Yep.
Yeah, just add one point about this issue of mills, which I think is really quite important, because the use of water and subsequently wind is just one of the ways in which people try to exploit non-human energy, try to get nature to do the work for you so that you don't have to work so hard. And in some sense, the ultimate purpose of technology is to reduce human effort. One of the truly remarkable things that start to happen in Europe around 900, or maybe a little bit before as well, is the reinvention of the horse. Now, the horses themselves probably didn't change all that much, but the way in which they were used by medieval Europeans compared to the way they were used by the Greeks and the Romans changed a great deal on account of 2 or 3 truly momentous inventions that turned the horse from a somewhat ineffectual accompaniment of armies and something that you did races with, to a pivotal element in the European economy, in agriculture, in pulling plows, but also in manufacturing, in transportation, and everywhere else.
And in war.
And in war, of course. And these inventions include the invention of the stirrup, which makes it much more... invention, of course, isn't quite right. The stirrup had been known in the Middle East, in the steppes of Central Asia, found its way to Europe through routes we cannot really track. All we do know is that by the Battle of Poitiers in 732, the French knights ride horses, and successfully so.
So that when they strike somebody with their lance, they don't simply go backwards off their horse because they've got their feet well locked in the stirrups.
Exactly, exactly. And this is something the Romans couldn't do, and neither could other people who had cavalry, like the Parthians, and so the cavalry were shooting arrows at people and then ran away, but there was none of this hand-to-hand combat that we associate with the Knights of the Round Table and so on and so forth. The other invention is probably even more important. That's the horse harness. That is to say, the Romans used horses to pull carriages, but they put the harness around the neck so that when real force was being exerted, it choked them.
It was as if... Yeah. So it was as if we were trying to pull a load attached to the end of our tie, so that the harder we pulled the load, the more we cut off our breath and strangled as a result. That was what was happening to the horse in classical antiquity, in the ancient Mediterranean world, because it had a strap that went across its throat. So the more tractive effort, the more the poor horse strangled itself.
Exactly. And the third thing that the Europeans start doing is shoeing their horses. Now, you could argue that this wasn't all that necessary in the Mediterranean, where the soils tend to be dry and sandy. But as soon as you start running horses on the wet clay soils of Northern Europe, the horse hooves start rotting away if they're exposed to sufficient moisture, and you need to keep them together by horseshoes. Now, horseshoes are made of metal, and this, of course, then feeds back into the need of making better iron, better nails, people who specialized in doing this, blacksmiths and so on, who then obviously are also the people who make better swords and daggers and so on. And so, but the use of horses as a source of energy takes a huge leap forward. And
for the West, who of course are doing it rather later than they did in China.
Indeed.
The Chinese had efficient horse collars, which enabled the horse to shove as hard as it possibly could since the beginning of the Christian era. You can see, if you look at pictures of, say, a Greek or Roman chariot, in which you might get a couple of people standing in a rather light little frame, and compare it with a Chinese chariot, which may have several people in it and a little house on top of it. The Chinese chariot is a bus compared with what the Greeks or Romans could have.
Yeah, indeed. But what then happens as Europeans become more and more dependent on horses and oxen as well is that the entire agricultural system has to change, because the fundamental problem in European agriculture, paradoxical as this may sound, is not just how to feed people, but how to feed the animals. Because, obviously horses and cows and oxen eat a lot, and in some sense, perhaps the central invention of the modern Middle Age, of the early Middle Ages, is an agricultural system that integrates the problem of how to feed people with the problem of how to feed animals, because it is being recognized that animals are essential to the arable product that Alan talked about earlier, not only because the plows are too heavy for people to pull, but also because animals provide you with protein products that are difficult to secure elsewhere, and animals then feed back into the fertility of the soil, because they are being, because their droppings are being used as a fertilizer. And so it is a very subtle, a fairly complex interaction between arable agriculture and husbandry that produces a system that by 1100, maybe even 1000, is more or less in place in many areas of Western Europe, and it is something that you will not see in the Europe controlled by the Roman Empire. It's quite different.
Is it also an advantage of that complex arable pastoral system that it can be extended at the less productive margins, so that Northern and Eastern Europe can be brought under the regime of the horse and ox and plough? In other words, relatively unproductive land under classical agricultural systems can at least support populations over an increasingly wide territory which up till then had not been farmed at all.
Absolutely, absolutely. And this is what happens. Europeans expand into areas of what we would think of today as Eastern Germany, Poland, Central Europe, which previously just couldn't be farmed. They were just forest. And what they do, one of the things that they do with animals is there's a huge deforestation going on in Europe, where forests are not only cut down, but the stumps are being pulled out. Now, this is actually not a trivial technical problem. It's easy to cut down a tree. Pulling out the stump so that you can actually use that land for farming requires typically animal power. And so once more, here's a role for animals to carry out. But then, of course, animal fertilizer is then used to keep these lands continuously fertile. They devise a variety of very clever crop rotations, including things like beans, which then and certain crops that restore nitrogen into the soil. Also, they didn't know that, but that's what these crops do. And what emerges is an agricultural system that is, I wouldn't want to compare it with China, because I'm not sure if you can compare at a level of sophistication two systems that produce different crops. That seems to make no sense. But clearly, and without any hesitation, I say that the kind of agriculture that we observe in Europe around the beginning of the second millennium, 1,000 years ago, is vastly more productive, more sophisticated, and in some sense better designed than anything that the Romans and the Greeks ever had around the
What about the implication that the kind of system you're talking about relies less and less and less on irrigation? That, I mean, there's a well-known argument that there's a very strong relationship between systems that rely on permanent irrigation, maintenance of canals, wet rice systems, and a certain need for coordination and central control. Whereas in the system of grain elevation, which feeds people and their animals, and then uses what the animals produce both to feed further people and also to fertilize the soil and produce more grain, that whole system can develop in ways which again makes it easier for relatively autonomous units to survive.
Yes.
Whereas in systems that rely on complex irrigation, it's less easy to be autonomous. What do we think of that argument?
I don't know. My problem in hearing about that comparison with China is that it isn't the case that the majority, even of Chinese wet rice agriculture, has depended on complex canal systems to get the water there. Very often it depends on the use of such water as is already flowing in natural courses and is provided by rain. So I don't think that's going to give us a key to a major east-west difference. But it certainly would give you perhaps a key to ways in which the West is changing through the introduction of those systems, certainly, with the ability to go off and open up new land and pull up the stumps and so on. Another thing I've heard of, I don't know whether people would agree with it, is that as you go over from using oxen for ploughing, relatively slow-moving animals, to using horses for ploughing, it has some advantages for peasants in that you can get bigger villages.
Yes.
Because the horse can walk so much more quickly down the lanes to a distant field in which you're going to work it today. So people in this village can work round all the way around it there. Whereas if they had oxen, some of them would have had to live near those fields, and some of them near that one, because otherwise you'd have taken all day to walk the oxen to these fields. And living in a larger village is nice.
Yeah,
You know,
so
there's a
oxen-
church and so on.
Oxen have advantages. They are cheaper and they're easier to feed. Throughout the Middle Ages, actually, we see an interesting phenomenon. We see the coexistence of these two different techniques, oxen and horse. It's a bit like, say, internal combustion engine and diesel engines today. Neither of them is sufficiently much better than the other to push them out the way the steam engine, say, has been pushed out. And I also, about hydraulics, I would like to point out that the problem in much of Europe, of course, is that they don't have to irrigate because the problem is they have too much water rather than too little. And that drainage is, in fact, a serious problem. There are parts of Europe, even in the early Middle Ages, where they are conquering large amounts of land from water, particularly in the Netherlands. And this requires a fair amount of coordination, and yet the Netherlands did not turn into a hydraulic despotism state, as far as we can tell.
It would be rather small, I
It would be rather,
Yes.
it would be rather small for that. In fact, the interesting thing is that the pioneers in much of this hydraulic engineering are monks.
Yes, the Cistercian monks, and they introduced a whole series of new innovations, a lot of new crops, rotations, drainage schemes. They were the really, really interesting innovators in this whole
So
area.
that fits well into Alan's story about the way in which monastic, relatively
Yes.
isolated monastic systems build monasteries near water. They become sites of further innovation.
Well,
and
Fountains
land
Abbey, for example, in Yorkshire, which is a Cistercian house, has lots of water flowing right through it in all sorts of ways, to scour the latrines, to drive the mills, and so on.
and
It was
also
a,
raise fish.
yes, but it was also possible to coordinate labor much more easily in a system that was dominated by a religious order, and to set up the systems for organizing the introduction of new techniques like that. And it did take some time for this to diffuse outward into areas where labor had to be coordinated in that way.
So, one of the things that puzzles me, particularly if you look at a place like Japan, where the wheel almost disappears, water wheels and other wheels of power disappear through Japanese history. They used a bit in the beginning. There are hardly any development of water power in Japan in that way, likewise windmills. Now I wondered, why is it that the West gets more and more interested in animals, water power, wind power? And my picture of Japan is that. Is it also true of China?
I can't say why the West do things that China doesn't do. One thing that I would draw attention to is the fact that, of course, the Chinese are very successful in using water power for a large number of purposes. Not least, of course, raising water to higher levels through clever arrangements of water wheels that have got containers on them that are driven up as the water wheel rotates and empty themselves at a higher level. Those are glorious.
Yeah.
But if you look at applications of water power in China, you find some very interesting ones quite early, particularly in connection with the triumphs of early Chinese metallurgy. Again, around the beginning of the Christian era, the Chinese are applying water power to producing air blasts for the metallurgical furnaces. And that certainly is very much a Chinese first. So if you want to say, can they make use of this power and they want it, they certainly can. And during the Tang dynasty, the great from 600 to about 900 AD, the great age of Chinese Buddhist monasticism, you find in parallel with the setting up of mills by Western monastic orders, that certainly the great estates of Buddhist monasteries have got lots and lots of water wheels, to the extent that the government finds itself receiving complaints from people. These monasteries are clogging up the waterways with their wheels and stopping anybody else making use of it. So, again, there's no sense in China that using mechanical power from water is something the Chinese are not interested in.
But what strikes one is they have all these things. They know about them. They have the technologies usually several thousand years before the West. But gradually, as in the case of glass, and as in the case of the wheel in Japan, and as in the case of animals in Japan, it stays either level or begins to decline. So our picture of 19th century China is not of a world filled with hundreds of water mills or windmills or extensive use of horses and animals. It either has faded away or is just not developed.
Certainly a 19th century Western observer would not have found China anything like so mechanical and animal using a place as the places where he or she had come from. But I think that's largely a question about the West rather than about a mystery about China deciding to give something up that it had been good at before. I think we have to ask the question of why the West did what it did, rather than to sort of say, goodness gracious, why didn't the Chinese go on and do the same thing?
I think that's absolutely right. I mean, to caricature it completely, I would say one of the key dates in the last 1,000 years, which one needs to think about, explain European difference, is 1775, because in that year, the Paris Academy of Sciences, the chief intellectual organization of the largest state in Europe, decided to ban any further discussion of two great problems: the production of gold by alchemists and the production of perpetually moving machines by engineers. And it seems to me that that's a symbolic date for the West, because it's at that moment, obviously I'm caricaturing for effect, but it's at that moment that what it means to be an expert is that an expert can tell you what you cannot do. He isn't any longer going to offer you dreams of endless profit. He isn't any longer going to say, I have a scheme here which will, using a very complicated water wheel, allow you then to drive a further set of mills without any expense whatsoever, guaranteeing you permanent profit.
Because the water goes back up again.
Because the water
and comes back round and does it, so the job goes on
once
forever.
the French engineers had decided, they don't, by our lights, have any reason so to decide. The physics theory, which explains why you can't have perpetually moving machines doing work, isn't actually going to be developed in Europe until the 1850s and 60s. But already in the 1770s, the French and the Brits decide there's no such thing. There are limits to what you can get out of the world, and we, these highly trained experts, can advise you on what those limits are, and therefore what a reasonable investment opportunity is. And where this matters most, no question, in the 18th century, is water wheels. Certainly in the area with which our riddle begins, that is to say, Lancashire. Because in Lancashire you have plausibly useful drops of height down which streams flow, especially in the area around Manchester. And they can drive mills. And for the 30 or 40 years before this great decision that there are no such things as perpetually moving machines, French and British engineers do extremely precise experiments on the most efficient possible design for a water wheel. Should it be powered by having the stream run over the top of it, and then it will work by impact. The water will push against the wheel, and so it will turn like this. Or should it be undershot and thus work by gravity, right? Well, highly precise experiments are done at the Royal Society by the civil engineers in Paris on the comparative advantages of overshot and undershot wheels. It turns out that overshot wheels are much more efficient. Overshot wheels spread like wildfire through Lancashire, and all of a sudden you have a vast increase in the efficiency, therefore the productivity, therefore the profit of the systems driving the new mills. Now, once you realize that that kind of thing can happen in 18th century Europe, and that in many ways it's a negative decision, it's a decision about limits, it's a decision about efficiency, it's also a decision about what techniques you can use to determine efficiency. I think you can see that over the millennium now that we're interested in, what we have to explain at least is how did an attitude and a set of technologies like that emerge around water wheels, which I suppose we do not find in any other culture. So if we think, if that's the question, what's the answer?
Can we just move on a little to the question of whether it's an advantage to be disadvantaged or advantaged? When I talked about rice as a miracle crop, highly productive, easy to cook and so on, that is one of the great advantages of Asian civilizations. And you can put forward the argument that the natural ecology, the plants and animal species in Asia were so good that in the end it, from our perspective now, led to a stability, whereas in the West it was the absence of really effective plants of certain kinds. Now, we've talked about rice. Another one is the paper mulberry. The fact that Japan and China had a wonderful tree which would grow paper, whereas in the West you had to have cloth paper at the beginning, and this leads you immediately into milling. You have to have fulling mills to pound the cloth. So you need machines because you don't have good paper making stuff. Another example would be bamboo. Bamboo is a wonderful plant. It grows very quickly, easy to cut and so on. And it's also very, very flexible. You can make tiny strands of it very easily indeed. And you can weave it into 1,000 uses. You can make it into houses, hats, umbrellas, whatever you like, almost anything. So with paper, bamboo,
because it's a
and
free
rice.
tube, it's a free pipe. You can draw the sceptre out.
That's right. You can puff out of it. I mean, its shape is and its versatility. It's really a miracle plant. So if you have paper, bamboos, and rice. On the other hand, in the West, you have to fight for these things. The equivalent of bamboo is iron. You have to fight for your iron, for your strong things.
If you want a tube, you've got a really difficult job
Exactly.
to make a tube in the West.
Yeah, I think if we compare bamboo to iron, which seems almost inevitable, one of the interesting things that occurs with mining in general, particularly coal and iron mining, is that because it's underground and because this is Europe where there is water, you have to pump. And I think pumping, much mundane as it sounds, actually defines to a great extent, and it's almost probably as important as clocks and as glass in requiring a very high levels of mechanical skill, craftsmanship, precision, and ability to work with materials. In fact, the first steam engine, as is well known, functioned as pumps. And why do Europeans have to pump? Because much of the good stuff is underground. It doesn't grow on top.
On trees.
And it doesn't grow on trees. And I think the correlation between the need to pump, whether you have to sort of pump out the land from away from the sea, as the Dutch had to do, or pump out water from coal mines, as the British had to do, does seem to correspond quite nicely with the development of a lot of engineering and mechanical skills that then turn out to be useful for other uses as well.
So in 18th century Europe, especially in France and Britain, you have experimenters posing very precisely the issue of the efficiency of water wheels. They build models to test it, they give numbers so they can give their clients reasonable estimates of the efficiency and therefore the worth of investing in one kind of design rather than another. And I think that's key to a certain European difference, which is this. Why is it that in Western Europe of this period in the 18th century, you have the apparently enormous necessity to make sure that the scheme in which you're investing, in this case water wheels, is going to offer a return, and you have methods to produce a reliable estimate of the worth of that strategy, and apparently in the East and elsewhere you don't find such strategies. It seems to me that's a fundamental question about the last millennium or so.
People are certainly not in China, by and large, applying quantitative experiment and investigation to the utility of different sources of power from water. That's certainly true, as far as I know.
Joel, why not?
I think by the late 18th century, the way Europeans treat their knowledge of the physical world around them has been transformed to the point where somebody in the middle of the 16th century wouldn't recognize it. It is not only that Europeans perfect something like what we call today an experimental method, in which you don't take anybody's word for it. You go out and try it yourself, and experiments are supposed to be reproducible. Everything that people report is verifiable. I think there's something deeper going on, which is really around by 1775, and that is the concept of an open science, in which knowledge about the physical world is not kept secret anymore. It is not kept a monopoly of a few, but as soon as something is being discovered, you advertise it to the world, you publish it.
But that's the way of making it your property, because you are the one that publishes
You
it.
are the one, but everybody has access.
So it depends on the Chinese invention of printing, of course.
Of course it does. But by that time, people have access. And I think a decision in 1775 to say, look, certain things are impossible, are based on the notion that if they had been possible, we would have known about it, because this knowledge would have been diffused. Okay? So it isn't like they can be ontologically certain that this can't be done. It's just that they say, look, we've been trying this for hundreds and hundreds of years, and given the concept of open science, we would have found out about it, and so therefore the likelihood it can be done is vanishingly small. That's one way in which European science develops, and certainly without that, it is very hard to see how we would have gotten to the next stage, which follows your 1775 declaration of impossibility, so to speak, quite close, and that is the development of Lavoisier and modern chemistry, which isn't around yet at that time, but is about to become the next stage. And surely when these developments are made, they spread like wildfire. Within a few years, everybody knows about them, and people try to reproduce them and struggle with the new concept and realize that this is for real, this is true, and we can do things with it. And I think in that regard, we need to emphasize that what I think creates the divergence between East and West at some point after the great discoveries is what we commonly refer to as the scientific revolution. Not so much because what the scientific revolution, methodology of acquiring and disseminating knowledge about the physical world, which it creates. And without that, I think eventually either there would have been no industrial revolution at all, or the industrial revolution would have petered out pretty quickly after it occurred, so in a similar way as earlier industrial revolutions had petered out.
I think
It's often been put. Why, with all that technological fertility, was China not the place where the Industrial Revolution happened? Efforts have been made to answer that by trying to find factors which in some way inhibited or stopped China having an Industrial Revolution. But I think scholars today would very largely want to deny that it is a legitimate question at all, and say that it's more or less like asking why there are no unicorns nowadays. There just aren't any unicorns. It just, the Industrial Revolution did not happen in China. And it's quite clear from China's previous technical fertility that having an Industrial Revolution is not about having some kind of special mechanical genius in your nation for being technologically inventive, because the Chinese had had plenty of that. It must perhaps depend on some rather specific things that happen in particular times and particular places in a very chancy way.
I think that sounds right. I mean, what I would want to underline, both in response to Joel and to you, is sure, there's something like an experimental method which begins to be institutionalized in Europe in the 17th century, and sure, the right way to ask this question is, you know, what are the positive factors producing this set of remarkable developments in Northern and Western Europe, rather than, you know, what's holding everybody else back. That's got to be right. One of the things that I would want to bring forward a great deal in answer to my own question is the notion of accounting. It's not just that experimentation is being done, but the supposition is that God is simultaneously, God the creator of this world is simultaneously a technician, he's an artisan, but he's also someone who counts. And that in the case of Western and Northern Europe, he's provided an environment of extremely scarce resources. And being an accountant, when you're dealing with water power, or human labor, or what chemical manipulation can produce, turns out to be a very successful strategy. So if one's thinking about what the civil engineers do with water wheels, or what the French chemists do with mineralogy and alchemy, or indeed what the engineers and natural philosophers working around pumping, such as Galileo himself, work on, they think these are accountancy problems. They think that because these resources are very scarce and extremely difficult to manage, and the costs of failure are enormous, very marginal advantages are worth securing. And therefore, counting up what you've got and trying to maximize the utility of what you've got, and doing that again and again until you can guarantee even a small return, that turns out to be a practical way of surviving, let alone succeeding, in a relatively hostile, very chancy and rather dark world. So I think it's precisely a pessimism about nature which goes along with this confidence in human capacity accurately to know what nature can do.
Obvious area which we ought to look at is weaponry and guns and gunpowder, because it clearly is one of the things that begins to differentiate Europe from Asia. And it also has such a strange riddle at the center of it, which is that the nation which invented gunpowder and earliest developed it somehow then didn't develop it in the aggressive and horrific way in which it was developed in Europe and finally triumphed over much of the world. So we need to look at the story of weaponry. Can we take it from China first of all, Christopher, because there is this puzzle.
I think it's worthwhile looking back a bit earlier than gunpowder weapons, actually, to earlier Chinese weapons technology, which was certainly highly efficient. What I have here is the working bit of a Chinese crossbow, which was the standard weapon, the standard infantry projectile weapon for Chinese armies at about the time of the Roman Empire. We're talking about something about the beginning of the Christian era. And this particular device was mass-produced by the imperial workshops, and each one of them has on it an inscription telling you when it was made and by whom. This one tells you that it was made in the 4th moon in a year corresponding to 88 AD by somebody, presumably the official in charge, Wang Hui, and that it was made for a particular troop of soldiers led by Zhou Ermin. It's even got a number 14 on it, just like if you look on your rifle, you see it's got a War Department thing stamped on it, a number. So the possession of sophisticated weapons employing the highest technology you can get. So this thing's a really beautifully made device. I pull the trigger and zonk, off it goes, and I cock it again, ready for the next one here. This shows the Chinese were very ready to produce the very best in military technology. There's no sense that they have a gentle and unwarlike philosophy here. So it's not very surprising when they turn out to be the first people to use gunpowder weapons. Gunpowder was discovered towards the end of the first millennium AD, to some extent by accident, by alchemists who were looking for an elixir of life and discovered that mixtures containing sulfur and potassium nitrate had interesting properties. But by 1044 AD, a bit before the Battle of Hastings, the Norman invasion of England, we have the first full description in a Chinese military manual of how you make gunpowder. And at that stage, it's used essentially as an incendiary substance. You throw a packet of it towards the enemy with a fuse and it goes off whoosh. Maybe you stuff it into, well, a bamboo tube and it squirts out like a flamethrower at the enemy and so on. If you can imagine, you have this packed with gunpowder, you have it also packed with bits of junk as well. And you're trying to climb up my city wall and I squirt this towards you, it discourages you somewhat and so on. And then of course there is the fact that if it's really got a good charge in it and I happen to hold it rather weakly, it may shoot off backwards and then I've got a rocket, which is of course another Chinese invention. It wasn't until round about the period of the Mongols in the 13th century that we really begin to say we're getting the appearance of things we can call guns, that is metal tubes usually, that actually fire a chunk of stuff out of the other end. But once those guns do appear, of course it's the Mongol period, there's great contact between East and West, they certainly spread very rapidly. And the interesting point from the comparative history of civilizations is that when those weapons get to Western Europe, which is in a very highly divided political situation with a great deal of competition between a number of entities, not just between countries, but within countries, with, say, royal power trying to build itself up above the power of the feudal lords and so on. People are desperate to improve these weapons very quickly, and do so, with the result that when, in the 15th century, Westerners sail ships with those weapons into the Indian Ocean, the sort of gunpowder weapons they meet are still the sort that might be useful for anti-personnel purposes from ship to ship. But the sort that the Westerners are bringing with them are things that can shoot projectiles long range, so you can lie offshore and blast a port into smithereens without them being able to touch you. A result of this intensive competition in a dangerous, divided and perhaps rather underdeveloped Europe, something that wasn't happening in China, where there was nothing like the same amount of pressure to make these weapons as good as possible.
That's very interesting.
I mean, for example, the great guns which the Turks used to demolish the walls of Constantinople in 1453 were not, in fact, brought from the Middle East, but from a group of Hungarian gunners who were hired by the Turkish ruler to fight against the Greeks inside the walls of Constantinople. And that tells you something about the extraordinary speed. I mean, essentially a century.
They fired a ball about that far across, didn't they?
Yeah,
These things,
yeah.
vast stone balls it would have been.
Yeah.
And we mustn't forget the spectacular uses of gunpowder in China for fireworks displays.
Yes, it has to be said that it is entirely fictitious to say, sadly, that the Chinese were so moral and good that they invented gunpowder but only used it for fireworks. I'm afraid at the very beginning they are using it, as the rest of us would, to kill one another.
I think, I mean, this seems to be one of the puzzles which is a little easier to solve because, firstly, as you say, the internal competition within China or within Japan is so small that the gunpowder weapons don't develop. Secondly, the absence of the development of sea power in a later period, the cannons of the ships that Europe tended to send out into the Atlantic is obviously one of the spurs to the development of cannon, and on the whole, with the gradual retreat of China and Japan from long-distance trading and exploration, then cannon on ships were not so necessary. But if you look at, I mean, the example of what you're saying is if you look at Venice, I visited the Arsenal. Well, we think of the Arsenal now, the word suggests not only a football team, but also a place where you make weapons. Well, it wasn't just a weaponry, it was a factory. It comes from Arabic again for a factory. And it's a vast, it was perhaps the biggest factory in the world in the 14th, 15th centuries, producing ships at the rate sometimes of a ship a day on a conveyor line with a division of labour between them. And I was enormously impressed by this very advanced attempt to make weapons of destruction to fight other nations with, and which was the basis of the Venetian Empire. And already you've got Venice against the Turks, you've got Venice against other European nations. So all the time you've got this competition between small states, as you say. And if you looked at weapons in Japan, which I know better, you find the best swords and weapons of Japan are made about the 12th, 13th century. Wonderful samurai swords. You look about 500 years later, wonderful samurai swords, not much different, and suits of armor, not much different. When the West comes in with its great black warships from America in the middle of the 19th century, this is the culmination of 500 years in which the weapons have been changing constantly and very quickly, all the time.
And increasingly scientifically. We have lovely devices like this artillery officer's calipers. What are the things you can do with this, Simon?
Well, this is an 18th century English device which you used, if you were an artillery officer, to measure the exact size of a cannonball and then the size of the barrel which you were going to put the ball in. And it has mathematical tables engraved on front and back which, most importantly, tell you that for a given weight and range, this is how much gunpowder you should put in the charge. Now, what this shows you, I mean, I think the comparison with China is extremely interesting. Again, what this shows you is an accountancy of killing. It would be odd to use this sort of on a minute-by-minute basis on the battlefield. What this kind of device is all about is the adoption of the Venetian arsenal model by the great northern European powers, especially the 17th century Netherlands, Britain and France, in which you get very large training institutions for gunners. Gunnery has an intimate relation with the new science of mechanics and above all of ballistics, in which you get faltering but in the end extremely important steps towards standardization. And it seems to me that that relationship between training and discipline, building enclosed military institutions of training, which are highly professional by the 17th and 18th century, highly examined and rigorous, and then the reliable production of very large numbers of extremely precise mathematical instruments, not only gunners' calipers like this, but devices like this. This is called a trammel, which could measure, again, 18th century device, which could again measure lengths to extraordinary precision. Now, I mean, I think that these objects have object lessons for us in thinking about the problem of artillery and Western specificity, because on the one hand, rapid changes in the technology of war demanded that you could think up material solutions like these artifacts. Once you have heavy iron cannonballs, especially on ships, and you cast gun barrels of a certain size, the catastrophic effects of getting your sums wrong go up exponentially.
The word is go up, certainly.
I mean, it's not just discovering a rocket when the bore blows up. You will kill most of your own men. So you need to be able to do these sums. And once you need to be able to do them, instrument makers have guaranteed markets now, because they know they can sell hundreds and hundreds of very precise and beautiful devices like this to every artillery officer in the country. So again, I mean, I don't think we should talk about the history of warfare as a kind of virtuous feedback, but there is this dynamic system in which more violence, more reliable violence, and more reliably monopolized violence is a very major factor in the production of precision, and vice versa.
And I think the important technological aspects of warfare have a very strong impact on what we generally think of as the diffusion of technology, because even relatively peripheral marginal states in Europe, if they wanted to play the political power game of being influential in Europe, they could not afford to fall back technologically, or else their armies would just be blown away from the field. And so this is particularly, I think, important in the continuous technological development in Russia, which is in late 17th, early 18th century Russia. The Russian Tsar, Peter the Great, comes to the conclusion that if he wants to maintain Russia as an important European power, he cannot afford to ignore the technology of the West. And in order to have cannon and ships that will do the job, he needs some kind of technical infrastructure in order to keep that going. And so what he does is he imports this wholesale from the West using the resources of the Russian state, not because he wanted technology as such, certainly not because he was interested in increasing the economic, because he was very much aware that unless he played the game of war using a cutting-edge technology, he didn't stand a chance in the battlefield. And this is, I think, if this is true for Russia, it must be true for other parts of Eastern and Northern Europe as well. And so from the European technological core, which is certainly by the beginning of the modern age, the Low Countries, Germany, parts of Germany, France, and the Low Countries, it spreads out to the rest of Europe, including, to some extent, to the Ottoman Empire, simply because of the continuous confrontation between these nation-states.
The other effect, which I think we should move on to, basically, to fire this cannonball you have to have a very accurate tube, as Simon has said, and you have an explosion which sends it down a cylinder. So you have the first single-cylinder piston engine, which is driving this out.
Absolutely.
Now, that creation of that iron technology which will make the piston, you could just pass me the bamboo there. Now, if you tried to make a steam engine, as it were, with this bamboo, it wouldn't work. The compression and so on would not work. You need very accurate iron boring. So, in many ways, this sad story of aggression and vicious behavior is the precondition for the development of the steam engine. Is
Absolutely.
that right?
I mean, pumps matter because the first stationary steam engines built in Britain, in the Midlands and in Cornwall, are essentially a wrapping together of the three technologies of cannon boring, distillation, and clockwork. And if you know how to put those three kinds of machinery together so that they don't blow up and they work more or less forever if you can maintain them, you can pump water in a way that suddenly makes all sorts of mining activities viable where they hadn't been before, and which again can only be explained if you think about what is the energy source. If you don't use these steam pumps, it's horses, and hence horsepower. So there seems to me to be this intimate systemic relationship between the military revolution of the 16th and 17th centuries, the critical role that horses have up till then played in making mining possible in certain ways, and the kinds of precision engineering that you get both in clockwork. I mean, you cannot have a stationary steam engine without an extremely good, very carefully engineered control device at the top of the pump, and that means you need a very good clockworking industry. And you also need something which can generate and maintain steam pressure. And that means brewing and distillation. We've not talked very much about the pleasures of life, but it seems to me step by step with the technologies of death are the technologies of consumption. And above all, it seems to me, in Western and Northern Europe, new ways of extracting alcohol from grain and grape, and ways of turning those into reliable, marketable commodities that you can, for example, produce all year round. Right? Can you have beer in the summer is a really important question for English people.
Yes.
And if you put those elements together, that is what the steam revolution of the early 18th century seems to me to be all about. It explains why it occurs, where it occurs. It also explains why it can be adopted very, very fast in the Low Countries, in Sweden, in the western parts of the German lands, and in northern France, and why it's much harder to introduce it in other parts of Europe, even though God knows it was tried.
Yes.
But turning now finally to the question of the extension of this forwards, we've seen, you've very nicely shown how all these things come together. They came together in Western Europe, but their future lay in the lands to which many of the poorer and disenchanted of Western Europe went, to America, because of course now America is the leading military power. Joel, can you suggest why it was that America took the military lead over the rest of the world, and the industrial lead?
Well, I think of all the important inventions that are made during and immediately subsequent to the Industrial Revolution, there's one that sometimes gets short-thrift because it isn't, you know, a gizmo you can hold in your hand and sort of show, look how clever this works, but it is, in some sense, something deeper, and that is, it's not just the idea of mass production, it is the technology of how to carry out mass production, which isn't quite the same. And this is something that emerges, it's actually known in the 19th century parlance as the American system. That is, in fact, a misnomer. Comes from Europe. The French were experimenting with interchangeable musketry before and during the French Revolution. It didn't come to anything, but they were trying. The idea was in the air. It's the Americans who carry it out. And the way they carry it out is by being able to achieve levels of accuracy and precision, both in dimensions and in the quality of materials that they use, to achieve something that gets closer and closer to the ideal of interchangeability. And today, manufacture would be unimaginable without interchangeability, right? If something breaks down in your car, you know, one of your spark plugs goes bad, you don't fix the spark plug. You take it out, you throw it away, you put in another one, because you know that the new spark plug that you're putting in is going to be absolutely identical to the one you've just thrown away, except that the other one is broken, this one is fine. And this is true for almost any mechanical part that we use today. And we keep forgetting how devilishly difficult it is to actually make parts from things that are fairly complicated, like spark plugs or motherboards for computers, to fairly simple things like screws and nails, and to make them so that they are truly identical, so that they fit. And once again, this actually leads us to the technology of war, because the first successful attempt in producing interchangeability is in gun manufacturing, and it is perhaps no surprise that this should occur in a nation that has always loved guns, namely the United States. And so what we now know is that interchangeability was not achieved instantaneously. It's a process that takes more than a half a century, even longer, to complete. But eventually the Americans pull it off. And why the Americans? Because what mass production in some sense involves, it's not quite true that it involves unskilled labor, sort of people who are just mindlessly standing at assembly lines and just cranking out enormous numbers of identical parts. It's more complicated than that. At the very top of the pyramid, there have to be extremely clever engineers, people like Eli Whitney, Simeon Norris, Oliver Evans, people like that, who are incredibly clever and who realize that the problem that they have at hand is something that requires mass production and all it entails. And what they build are a set of machine tools that allow you to achieve a level of precision that was hitherto really very difficult to attain. And so that if you produced something according to certain specifications with very low levels of tolerance, you could produce it over and over and over again. Now, you are going to do that in a country where skilled labor exists but is very expensive. But you're also going to do it in a country where the preferences of the consuming public are such that they don't mind buying a product that is exactly identical to the one that their neighbors have, which is something that you need for mass production. If you want custom-made clothes, a custom-made hunting rifle, you know, with your, you know, which is just, you're the only one who has one like that, okay? Then mass production isn't for you. But in 19th century America, people were willing to buy goods as long as they worked well, as long as they were relatively inexpensive, and as long as they were easy to maintain, because a lot of people live out there in the farm, and you know, and if my reaper breaks down, and I live in Iowa, and I have to order a technician to come in from Chicago, that's just not feasible.